A nuclear thermal rocket is a proposed spacecraft propulsion technology. In a nuclear thermal rocket, a working fluid, usually liquid hydrogen, is heated to a high temperature in a nuclear reactor, and then expands through a rocket nozzle to create thrust. In this kind of thermal rocket, the nuclear reactor's energy replaces the chemical energy of the propellant's reactive chemicals in a chemical rocket. The thermal heater/inert propellant paradigm, as opposed to the reactive propellants of chemical rockets, turns out to produce a superior effective exhaust velocity, and therefore a superior propulsive efficiency, with specific impulses on the order of twice that of chemical engines. The overall gross liftoff mass of a nuclear rocket is about half that of a chemical rocket, and hence when used as an upper stage it roughly doubles or triples the payload carried to orbit. A nuclear engine was considered for some time as a replacement for the J-2 used on the SII and SIV-B stages on the Saturn V and Saturn I rockets. Originally drop-in replacements were considered for higher performance, but a larger replacement for the SIV-B stage was later studied for missions to Mars and other high-load profiles, known as the SN. Nuclear thermal space tugs were planned as part of the space transportation system to take payloads from a propellant depot in low Earth orbit to higher orbits, the Moon, and other planets. Robert Bussard proposed the single-stage-to-orbit Aspen vehicle using a nuclear thermal rocket for propulsion and liquid hydrogen propellant for partial shielding against neutron backscattering in the lower atmosphere. The Soviet Union studied nuclear engines for their own moon rockets, notably upper stages of the N-1, although they never entered an extensive testing program like the one the U.S. conducted throughout the 1960s at the Nevada test site. Despite many successful firings, American nuclear rockets did not fly before the space race ended. To date, no nuclear thermal rocket has flown, although the NERVA NRX-EST and NRX-XE were built and tested with flight design components. The highly successful U.S. Project Rover, which ran from 1955 through 1972, accumulated over 17 hours of runtime. The NERVA NRX-XE, judged by SNPO to be the last technology development reactor necessary before proceeding to flight prototypes, accumulated over 2 hours of runtime, including 28 minutes at full power. The Russian nuclear thermal rocket Do-410 was also claimed by the Soviets to have gone through a series of tests at the nuclear test site near Semipalatinsk. The United States tested 20 different sizes and designs during Project Rover and NASA's NERVA program from 1959 through 1972 at the Nevada test site, designated Kiwi, Phoebus, NRX-IST, NRX-XE, PAWI, PAWI-2 and the nuclear furnace, with progressively higher power densities culminating in the PAWI and PAWI-2. Tests of the improved PAWI-2 design were cancelled in 1970 in favor of the lower-cost nuclear furnace, and the U.S. nuclear rocket program officially ended in spring of 1973. Current 110 kilonewtons reference designs are based on the PAWI, and have specific impulses of 925 seconds. Types: a nuclear thermal rocket can be categorized by the construction of its reactor, which can range from a relatively simple solid reactor up to a much more complicated but more efficient reactor with a gas core. As with all thermal rocket designs, the specific impulse produced is proportional to the square root of the temperature to which the working fluid is heated, and hence the most efficient designs require the highest temperatures possible. This is typically limited by the properties of materials. Solid core equals, the most traditional type uses a conventional nuclear reactor running at high temperatures to heat the working fluid that is moving through the reactor core. This is known as the solid core design, and is the simplest design to construct. The simplest of nuclear thermal rockets, solid core reactors are limited by the melting point of the materials used in the reactor cores. The solid core design needs to be constructed of materials that remain strong at as high a temperature as possible. Nuclear reactions can create much higher temperatures than the temperatures the materials can withstand, meaning that much of the potential of the reactor for very high temperatures is sacrificed. Even more limiting is the cracking of fuel coatings due to the large temperature ranges, and the necessity of matching coefficients of expansion in all the components. Using hydrogen propellant, A solid core design typically delivers specific impulses on the order of 850 to 1000 seconds, about twice that of liquid hydrogen-oxygen designs such as the Space Shuttle main engine. Other propellants are sometimes proposed, such as ammonia, water or LOX. Although these propellants would provide reduced exhaust velocity, their greater availability can reduce payload costs by a very large factor where the mission delta-V is not too high, such as within cislunar space or between Earth orbit and Martian orbit. Above about 1500 K, hydrogen begins to dissociate at low pressures, or 3000 K at high pressures, a potential area of promise for increasing the ISP of solid-core reactors. Immediately after World War II, the weight of a complete nuclear reactor was so great that it was feared that solid-core engines would be hard-pressed to achieve a thrust-to-weight ratio of 1:1, which is needed to overcome the gravity of the Earth at launch. The problem was quickly overcome, however, and over the next 25 years U.S. nuclear thermal rocket designs eventually reached thrust-to-weight ratios of approximately 7:1. Still, the lower thrust-to-weight ratio of nuclear thermal rockets versus chemical rockets and the large tanks necessary for liquid hydrogen storage mean that solid-core engines are best used in upper stages where vehicle velocity is already near orbital, in space tugs used to take payloads between gravity wells, or in launches from a lower-gravity planet, moon or minor planet where the required thrust is lower. To be a useful Earth launch engine, the system would have to be either much lighter, or provide even higher specific impulse. The true strength of nuclear rockets currently lies in solar system exploration, outside Earth's gravity well. One way to increase the temperature, and thus the specific impulse, is to isolate the fuel elements so they no longer have to be rigid. This is the basis of the particle bed reactor, also known as the fluidized bed, dust bed, or rotating bed design. In this design the fuel is placed in a number of elements which float inside the hydrogen working fluid. Spinning the entire engine forces the fuel elements out to walls that are being cooled by the hydrogen. This design increases the specific impulse to about 1000 seconds, allowing for thrust-to-weight ratios greater than 1:1, although at the cost of increased complexity. Such a design could share design elements with a pebble bed reactor, several of which are currently generating electricity. From 1987 through 1991, the SDI office funded Project Timberwind, a non-rotating nuclear thermal rocket based on particle bed technology. Although the project was cancelled before testing in 1992 by the incoming Clinton administration, the design was thought to achieve thrust-to-weight ratios of 31 and specific impulses of at least 1000 seconds. Liquid core dramatically greater improvements are theoretically possible by mixing the nuclear fuel into the working fluid and allowing the reaction to take place in the liquid mixture itself. This idea is the basis of the liquid core engine, which can operate at temperatures above the melting point of the nuclear fuel. The maximum operating temperature of the engine is determined by the maximum temperature that the container wall can withstand while it is actively cooled by the hydrogen. The liquid core design is expected to deliver performance on the order of 1300 to 1500 seconds. These engines are currently considered to be very difficult to build. The reaction time of the nuclear fuel is much longer than the heating time of the working fluid and therefore requires a method to trap the fuel inside the engine while allowing the working fluid to easily exit through the nozzle. Most liquid-phase engines have focused on rotating the fuel fluid mixture at very high speeds to force the fuel to the outside by centripetal force. The design mirrors the particle bed design in many ways but operates at even higher temperatures. Robert Zubrin has proposed an alternative liquid core design, the nuclear saltwater rocket. In this design, water is the working fluid and also serves as the neutron moderator. The nuclear fuel is not retained, which drastically simplifies the design. However, by its very design, the rocket would discharge massive quantities of extremely radioactive waste and could only be safely operated well outside the Earth's atmosphere and perhaps even entirely outside Earth's magnetosphere. Gas core. The final classification is the gas core engine. This is a modification to the liquid core design which uses rapid circulation of the fluid to create a toroidal pocket of gaseous uranium fuel in the middle of the reactor, surrounded by hydrogen. In this case the fuel does not touch the reactor wall at all, so temperatures could reach several tens of thousands of degrees, which would allow specific impulses of 3,000 to 5,000 seconds. In this basic design, the open cycle, the losses of nuclear fuel would be difficult to control, which has led to studies of the closed cycle, or nuclear light bulb engine, where the gaseous nuclear fuel is contained in a super high temperature quartz container, over which the hydrogen flows. The closed-cycle engine actually has much more in common with the solid core design, but this time is limited by the critical temperature of quartz instead of the fuel stack. Although less efficient than the open-cycle design, the closed-cycle design is expected to deliver a rather respectable specific impulse of about 1,500 × 2,000 seconds. History. Although engineering studies of all of these designs were made, only the solid core engine was ever built. Development of such engines started under the aegis of the Atomic Energy Commission in 1955 as Project Rover, with work on a suitable reactor starting at Los Alamos National Laboratory and Area 25 in the Nevada test site. 4 basic designs come from this project: Kiwi, Phoebus, Pui and the nuclear furnace. 20 rockets were tested. When NASA was formed in 1958, it was given authority over all non-nuclear aspects of the rover program. In order for NASA to cooperate with the AEC, the Space Nuclear Propulsion Office was created at the same time. In 1961, the NERVA program was created. Marshall Space Flight Center had been increasingly using Kiwi for mission planning, and NERVA was formed to formalize the entry of nuclear thermal rocket engines into space exploration. Unlike the AEC work, which was intended to study the reactor design itself, NERVA's goal was to produce a real engine that could be deployed on space missions. A 75,000-pound forces thrust baseline NERVA design was based on the Kiwi B4 series, and was considered for some time as the upper stages for the Saturn V, in place of the J2s that were actually flown. Although the Kiwi NERVA designs were the only ones to be tested in any substantial program, a number of other solid-core engines were also studied to some degree. The Small Nuclear Rocket Engine, or SNRE, was designed at the Los Alamos National Laboratory for upper-stage use, both on unmanned launches as well as the Space Shuttle. It featured a split nozzle that could be rotated to the side, allowing it to take up less room in the shuttle cargo bay. The design provided 73 kilonewtons of thrust and operated at a specific impulse of 875 seconds, and it was planned to increase this to 975 with fairly basic upgrades. This allowed it to achieve a mass fraction of about 0.74, comparing with 0.86 for the SSME, one of the best conventional engines. A related design that saw some work, but never made it to the prototype stage, was Dumbo. Dumbo was similar to Kiwi NERVA in concept, but used more advanced construction techniques to lower the weight of the reactor. The Dumbo reactor consisted of several large barrel-like tubes which were in turn constructed of stacked plates of corrugated material. The corrugations were lined up so that the resulting stack had channels running from the inside to the outside. Some of these channels were filled with uranium fuel, others with a moderator, and some were left open as a gas channel. Hydrogen was pumped into the middle of the tube, and would be heated by the fuel as it traveled through the channels as it worked its way to the outside. The resulting system was lighter than a conventional design for any particular amount of fuel. The project developed some initial reactor designs and appeared to be feasible. Between 1987 and 1991 an advanced engine design was studied under Project Timberwind, under the aegis of the Strategic Defense Initiative, which was later expanded into a larger design in the Space Thermal Nuclear Propulsion Program. Advances in high-temperature metals, computer modeling and nuclear engineering in general resulted in dramatically improved performance. While the NERVA engine was projected to weigh about 6,803 kilograms, the final STNP offered just over one-third the thrust from an engine of only 1,650 kilograms by improving the ISP to between 930 and 1,000 seconds. In January 2012, the propulsion group for Project Icarus began a technology development project, known as Project Bifrost, under the auspices of Icarus Interstellar and General Propulsion Sciences, to develop an NTR propulsion system, initially aimed at interplanetary missions. Test firings: Kiwi was the first to be fired, starting in July 1959 with Kiwi 1. The reactor was not intended for flight, hence the naming of the rocket after a flightless bird. This was unlike later tests because the engine design could not really be used. The core was simply a stack of uncoated uranium oxide plates onto which the hydrogen was dumped. Nevertheless, it generated 70 MW and produced an exhaust temperature of 2683 kelvins. Two additional tests of the basic concept, A and A3, added coatings to the plates to test fuel rod concepts. The Kiwi B series fully developed the fuel system, which consisted of the uranium fuel in the form of tiny uranium dioxide spheres embedded in a low-boron graphite matrix, and then coated with niobium carbide. 19 holes ran the length of the bundles, and through these holes the liquid hydrogen flowed for cooling. A final change introduced during the Kiwi program changed the fuel to uranium carbide, which was run for the last time in 1964. On the initial firings, immense reactor heat and vibration cracked the fuel bundles. Likewise, while the graphite materials used in the reactor's construction were indeed resistant to high temperatures, they eroded under the heat and pressure of the enormous stream of superheated hydrogen. The fuel bundle problem was largely solved by the end of the program, and related materials work at Argonne National Laboratory looked promising. Fuel and engine coatings never wholly solved this problem before the program ended. Building on the Kiwi series, the Phoebus series were much larger reactors. The first 1A test in June 1965 ran for over 10 minutes at 1090 MW, with an exhaust temperature of 2370 kelvins. The B run in February 1967 improved this to 1500 MW for 30 minutes. The final 2A test in June 1968 ran for over 12 minutes at 4000 MW, at the time the most powerful nuclear reactor ever built. In contrast, the Itaipu Dam, one of the most powerful hydroelectric plants in the world, produces 14,000 MW, enough to supply 19% of all the electricity used in Brazil, and 90% of that used in Paraguay. NERVANRX started testing in September 1964. The final engine in this series was the XE, designed with flight design hardware and fired in a downward position into a low-pressure chamber to simulate a vacuum. SNPO fired NERVANRX XE 28 times in March 1968. The series all generated 1100 MW, and many of the tests concluded only when the test stand ran out of hydrogen propellant. NERVANRX XE produced the baseline 75,000-pound forces thrust that Marshall required in Mars mission plans. A smaller version of Kiwi, the PAWI, was also built. It was fired several times at 500 MW in order to test coatings made of zirconium carbide, but PAWI also increased the power density of the system. An unrelated water-cooled system known as NF1 was used for future materials testing. PAWI became the basis for current NTR designs being researched at NASA's Glenn and Marshall Research Centers. The last NRX firing lost a relatively small 17 kilograms of fuel in 2 hours of testing, enough to be judged sufficient for space missions by SNPO. PAWI 2's fuel elements reduced fuel corrosion still further, by a factor of 3 in nuclear furnace testing, but PAWI 2 was never tested on the stand. Later designs were deemed by NASA to be usable for space exploration, and Los Alamos felt that it had cured the last of the materials problems with the untested PAWI. The NERVA rover project was eventually cancelled in 1972 with the general wind-down of NASA in the post-Apollo era. Without a manned mission to Mars, the need for a nuclear thermal rocket was unclear. To a lesser extent, it was becoming clear that there could be intense public outcry against any attempt to use a nuclear engine. Nuclear versus chemical, directly comparing the performance of a nuclear engine and a chemical one is not easy. The design of any rocket is a study in compromises and different ideas of what constitutes better. The outline considers the NERVA-derived engine proposed by NASA in the 1960s. Comparing it with the SIVB stage from the Saturn it was intended to replace. for any given thrust, the amount of power that needs to be generated is defined by, where T is the thrust and is the exhaust velocity. Can be calculated from the specific impulse, ISP, where, using the J2 on the SIVB as a baseline design, we have P equals 414 s, 9.81 m2 equals 2060 mW, or about the amount generated in a large nuclear reactor. However, as outlined above, even the simple solid core design provided a large increase in ISP to about 850 seconds. Using the formula above, we can calculate the amount of power that needs to be generated, at least given extremely efficient heat transfer, P equals 850 s 9.81 m2 equals 4227 mW. The ISP improvement demands higher energy. Given inefficiencies in the heat transfer, the actual NERVA designs were planned to produce about 5 GW, which would make them the most powerful nuclear reactors in the world. The fuel flow for any given thrust level can be found from. For the J2, this is M equals 1014 kN/414 9.81, or about 250 kilograms per second. For the NERVA replacement considered above, this fuel flow would be 121 kilograms per second. The mass of hydrogen is much lower than the hydrogen-oxygen mix in the J2, where only about 1/6 of the mass is hydrogen. Since liquid hydrogen has a density of about 70 kilograms m³, this represents a flow of about 1,725 liters per second, about 3 times that of the J2. This requires additional plumbing but is by no means a serious problem. The famed F1 had flow rates on the order of 2,500 liters per second. Finally, one must consider the design of the stage as a whole. The SIVB carried just over 300,000 liters of fuel, 229,000 liters of liquid hydrogen, and 72,700 liters of liquid oxygen. The SIVB uses a common bulkhead between the tanks, so removing it to produce a single larger tank would increase the total load only slightly. A new hydrogen-only nuclear stage would thus carry just over 300,000 liters in total, or about 21,300 kilograms. At 1,725 liters per second, this is a burn time of only 175 seconds, compared to about 500 in the original SIVB. The total change in velocity, the so-called delta V, can be found from the rocket equation, which is based on the starting and ending masses of the stage. Where is the initial mass with fuel, the final mass without it, and V is as above. The total empty mass of the J2-powered SIVB was 13,311 kilograms, of which about 1,600 kilograms was the J2 engine. Removing the inter-tank bulkhead to improve hydrogen storage would likely lighten this somewhat, perhaps to 10,500 kilograms for the tankage alone. The baseline NERVA designs were about 15,000 pounds, or 6,800 kilograms, making the total unfueled mass of a drop in SIVB replacement around 17,300 kilograms. The lighter weight of the fuel more than makes up for the increase in engine weight. Whereas the fueled mass of the original SIVB was 119,900 kilograms, for the nuclear-powered version this drops to only 38,600 kilograms. Following the formula above, this means the J2-powered version generates AIV of ln 119,900/13,311, or 8,900 meters per second. The nuclear-powered version assumed above would be ln 38,600/17,300, or 6,700 meters per second. This drop in overall performance is due largely to the much higher burnout weight of the engine, and to smaller burn time due to the less dense fuel. As a drop in replacement, then, the nuclear engine does not seem to offer any advantages. However, this simple examination ignores several important issues. For one, the new stage weighs considerably less than the older one, which means that the lower stages below it will leave the new upper stage at a higher velocity. This alone will make up for much of the difference in performance. More importantly, the comparison assumes that the stage would otherwise remain the same design overall. This is a bad assumption. One generally makes the upper stages as large as they can be given the throw weight of the stages below them. In this case one would not make a drop-in version of the SIVB, but a larger stage whose overall weight was the same as the SIVB. Following that line of reasoning, we can envision a replacement SIVB stage that weighs 119,900 kilograms fully fueled, which would require much larger tanks. Assuming that the tankage mass triples, we have AM1 of 31,500 plus 6,800 equals 38,300 kilograms, and since we have fixed at 119,900 kilograms, we get IV equals ln, 119,900 / 38,300, or 9,500 meters per second. Thus, given the same mass as the original SIVB, one can expect a moderate increase in overall performance using a nuclear engine. This stage would be about the same size as the SII stage used on the Saturn. Of course, this increase in tankage might not be easy to arrange. NASA actually considered a new SIVB replacement, the SN, built to be as physically large as possible while still being able to be built in the VAB. It weighed only 10,429 kilograms empty and 53,694 kilograms fueled. The combination of lower weight and higher performance improved the payload of the Saturn V as a whole from 127,000 kilograms delivered to low Earth orbit to 155,000 kilograms. It is also worth considering the improvement in stage performance using the more advanced engine from the SNTP program. Using the same SIVB baseline, which does make sense in this case due to the lower thrust, we have an unfueled weight of 10,500 plus 1,650 equals 12,150 kilograms, and a fueled mass of 22,750 plus 12,150 equals 34,900 kilograms. Putting these numbers into the same formula we get AIV of just over 10,000 mZa. Remember, this is from the smaller SIV-sized stage. Even with the lower thrust, the stage also has a thrust-to-weight ratio similar to the original SIVB, 34,900 kilograms being pushed by 350 kilonewtons, as opposed to 114,759 kilograms pushed by 1,112 kilonewtons. The STNP-based SIVB would indeed be a drop-in replacement for the original SIVB, offering higher performance from much lower weight. In summation, NASA's current reasoning is that TNP can be developed that would be twice as efficient as its chemical counterpart, though it is likely such an engine would only be used beyond the Earth's atmosphere. Risks: an atmospheric or orbital rocket failure could result in the dispersal of radioactive material into the environment. A collision with orbital debris, material failure due to uncontrolled fission, material imperfections or fatigue, or human design flaws could cause a containment breach of the fissile material. Such a catastrophic failure while in flight could release radioactive material over the Earth in a wide and unpredictable area. The amount of contamination would depend on the size of the nuclear thermal rocket engine, while the zone of contamination and its concentration would be dependent on prevailing weather conditions and orbital parameters at the time of re-entry. It is unlikely that a reactor's fuel elements would be spread over a wide area because the fuel elements in solid-core nuclear thermal rockets are designed to withstand very high temperatures and high pressures. They are composed of very strong materials such as carbon composites or carbides and are normally coated with zirconium hydride. Conventionally, the solid-core NTR fuel itself is a small percentage of U-235 buried well inside an extremely strong carbon or carbide mixture. The radioactivity of these elements is quite low and would pose a minimal hazard unless the physically small reactors have been run for an extended period. Kiwi TNT In January 1965, the U.S. rover program purposely placed a Kiwi reactor on fast excursion to simulate a worst-case scenario of a fall from altitude into the ocean such as might occur in a booster failure after launch. The rocket was positioned on a railroad car in the Jackass Flats area of the Nevada test site, with the reactor specially modified so as to go prompt critical. The radiation released would have caused fatalities out to 600 feet and injuries out to 2,000 feet. Current solid-core nuclear thermal rocket designs may greatly limit the dispersion and breakup of potentially radioactive fuel elements and thereby confine the overall hazard from the elements to near the launch site and reduce it to a level that would be lower than the many open-air nuclear weapons tests of the 1950s. Current research, at its Marshall Space Flight Center, NASA is simulating nuclear thermal rocket fuels with the interim goal of developing a nuclear cryogenic propulsion stage in support of the Space Launch System. The project could see rocket stages twice as efficient as their chemical counterparts propelling crewed missions to the Moon, Mars and beyond. See also, in situ resource utilization, nuclear pulse propulsion, radioisotope rocket, spacecraft propulsion, thermal rocket, UHTREX. Fission fragment rocket. Nuclear rocket projects NERVA, Project Orion, Project Pluto, Project Rover, Project Prometheus, Project Timberwind. References. External links, Nuclear Space Propulsion, NASA 1968 on YouTube, Dumbo, picture of the X-engine, Rover Nuclear Rocket Engine Program, Final Report, NASA 1991. Neo-fuel proposal for steam-based interplanetary drive, using off-Earth ice deposits, Project Prometheus, Beyond the Moon and Mars, Nuclear Propulsion, RD-0410 USSR's nuclear rocket engine, Soviet-Russian solid-core nuclear rocket engine.